In the late 19th century, laboratory experiments and cosmic observations showed that classical mechanics was unable to explain high speeds and subatomic particles. Classical physics suffered a crisis and the conditions for the emergence of modern physics were provided. In classical mechanics, which was formulated to explain the macroscopic world, all objects, even stars and planets, were considered particles. These particles behaved like points in the equations, which were called point-like. When the classical concept of a particle as a point-like entered modern physics, its problems became apparent. In addition, the wave-particle duality made its intuitive understanding and explanation more complicated. The wave function or Schrödinger equation in quantum mechanics is similar to Newton's second law in classical mechanics. Bohr calculated the location of the electron in his atomic model using Newton's second law. In fact, the particle considered by Bohr was a classical particle, while the Schrödinger particle was a wave particle in quantum mechanics. The difference between a classical particle and a quantum particle is like the difference between the two formulas of Newton's second law and the wave function. Experimental observations show that the fundamental components of nature are not discrete particles, rather, they are fields. The most familiar of these fields is the electromagnetic field. And a photon is a packet of an electromagnetic wave that is resulting from the excitation of the electromagnetic field. The same process happens for other particles. The electron is the excitation of the electron field. Similarly, each of the fundamental particles is an excitation of its own field. In fact, each particle is the concentrated field associated with that particle. Field excitation is not the only definition of a quantum particle. Various definitions have been provided for it, and even some physicists avoid the definition of particle. And the particle is considered pure mathematics that is used for calculations in physical realities. However, many efforts have been made to provide a definition of the particle that both plays its role in mathematical equations and is compatible with laboratory observations. A particle is a collapsed wave function. In quantum mechanics, superposition is the ability of a quantum system to be in multiple states simultaneously. Here the system is a quantum particle. When we observe or measure a particle, its wave function collapses. In other words, until a particle is observed, it is not a particle and is a wave function. A particle is an irreducible of a group. The theory of quarks showed that some particles have common characteristics and differences that physicists divided with color and flavor labels. In addition, there is a property in quarks called color confinement that participate in binary or triple combinations. Physicists use mathematical symmetry groups to describe them. With this classification, the particle is a state of the group that is irreducible. In fact, this is not a definition of a particle, but a way to describe the properties of a particle. Strings. In the 1970s, since quantum field theory did not include gravity, string theory entered physics and one-dimensional strings replaced point-like particles. One of the many vibrational modes of the string corresponds to the graviton, which carries the force of gravity. According to the proponents of string theory, if we magnify the particles enough, we will reach one-dimensional vibrating strings. String theory also could not solve the problem of modern physics, as it has not been solved so far. Two brilliant opinions have appeared in the minds of contemporary physicists who have presented the image of particles in a new way. A particle is a metamorphosis in an ocean of qubits. The qubit is the basic unit of quantum cryptography, which is probably a combination of two states of 0 and 1 and is considered the fundamental unit of information. So, the statement "it from qubit" became a slogan. This slogan provided the basis for efforts and research that led to the emergence of the hypothesis of the deformation of qubits. In this hypothesis, entangled qubits stitch together the fabric of spacetime, and spacetime has holographic properties. That is, all the information about a region of spacetime can be encoded in a lower dimension, often at the region level. The holographic principle says that gravity comes from thin vibrating strings, which are all holograms of a flat, two-dimensional universe. Another camp of researchers who call themselves amplitudologists seeks to return the spotlight to the particles themselves. These researchers argue that quantum field theory, the current lingua franca of particle physics, tells far too convoluted a story. We're trying to find these objects out there in the Platonic world of ideas that give us causal properties automatically, Arkani Hammad said. Then we can say, aha! Now I can see why this picture can be interpreted as evolution. The problem of fundamental particle physics. The laws and observations of quantum mechanics regarding particles are extrastructural. All properties attributed to particles, momentum, energy, electric charge, spin, color, and flavor are all extrastructural properties of particles, and physicists believe that fundamental particles are unstructured. But in recent years, this attitude has been doubted. In the CPH theory, using the photon behavior in the gravitational field, the structure of the photon was first defined. And then according to the mass-energy equivalence, and the structure of the photon, the structure of other fundamental particles was defined. I hope the content presented in this video was useful for you. Good day to you.